Everybody, welcome also from my part. My name is Rüdiger Frey. I'm currently at Vienna University of Economics and Business, and I had the pleasure of being a couple of very fruitful years in Zurich, a long time ago, 15 years ago or so, and that's where, together with Alex and Paul, we started the project to write a book on quantitative risk management, which is one of those projects which tended to keep us busy for much longer than we thought, and which is sort of still with us, but it turned out to be a success. Paul started to talk about the modeling of value and value change, and this has sort of two big sections, mapping of risk and valuation, and then we will go on in this morning section and talk about risk measurement. We were talking about, I go very, very briefly through these slides, which we had before the break. So we had a portfolio of financial instruments and denote by VT its value today, and we consider a given time horizon delta t, and we're interested in the change of the value over this portfolio. Delta VT plus 1 is VT plus 1 minus VT. And Paul explained the reasons. We're going to be mostly concerned with the negative change in value of the losses, essentially because this allows us to talk about upper tails and because QRM is mainly concerned with losses. The distribution of LT plus 1, as seen from today, is called the loss distribution with distribution function FL or F. And then we come to mapping. So if you want to model losses, this in the next few slides, they are really, I should say that they are motivated by applications to market risk, and the formalism was first developed together with this famous risk matrix approach, but the thinking and the formalism is useful also for other areas of risk. One issue you typically have when you want to model the value of a portfolio, maybe even of your whole trading book or something, is that you have to reduce dimensionality, and this is done via mapping, by modeling the value at time t as a function of time and a random vector of risk factors. Vt is a function of time and these risk factors, so this could be key interest rates, key exchange rates in a market risk application, certain factors that drive the evolution of your credit portfolio, so on. We be more specific about this on Wednesday morning when we discuss market risk in detail. Of course, when you apply this, writing down, that's the beauty of mathematics. You just write down an F and a Z and you do some theory with it. If you really want to do this in practice, you have lots of considerations to make. How far do you want to go into detail? Which risk factors are maybe important for the portfolio at hand? Which ones can be neglected? These choices are, as always in applied modeling, a trade-off between accuracy on the one hand and tractability on the other, and making good choices there is maybe the art in this game. And we come to this later. Now, the idea is we're standing at time t, we're interested in the losses over the period t plus 1, so let's say over the next day or the next 10 days to be specific. And for that, the important part is, you know, the current risk factor, the current value of the interest rate, exchange rate, the current state of the defaults in your credit portfolio, but we do not know how this is going to change over the future, and that's why we introduced the risk factor changes. Xt plus 1 is Zt plus 1 minus Zt, and this allows you to write the loss over the period Tt plus 1 as a function of these risk factor changes. Conceptually, that's very important. Mathematically, it's very simple. Lt plus 1 is minus the change in value, so that's the negative of the mapping at time t plus 1, risk factors at time t plus 1 minus f of t zt. And now you can, of course, write the risk factors at time t plus 1 as risk factors at time t plus the change in their value, so zt plus 1 is zt plus xt plus 1. The important part in this representation is that this guy here, which is also in orange, is the only thing which you do not know at time t. You know, okay, the mapping you know because you've chosen it. You suppose you know the risk factors at time t, so all that you know, that's the bit where the uncertainty is in. And hence, when you want to understand losses or the loss distribution at time t plus 1, essentially what you have to do is you have to estimate the distribution of this guy here, and you have to compute or simulate or whatever the distribution of this difference, so the distribution of f. This is essentially a translation, f of this guy here. And this is important in particular when we talk also about historical simulation. So since this is known, we can write LT plus 1 as some function L of xt plus 1, and L of x is just this difference. And if you want to be fancy, we call this the loss operator. I'm not going to do this a lot today, but when we talk about historical simulation in more detail on Wednesday, this will be quite convenient. Of course, if you're talking about, well, this is now very specific to market risk, this slide. If you're taking a small delta t, 1 day, 10 days, then typically these risk factors will not vary a lot. And then we can work with first order Taylor approximations. So the change can be approximated. F of t plus 1, zt plus xt plus 1 is roughly equal to the current value plus the change ft, that's the change in time, plus the derivative with respect to these risk factors, fz of tzt times the change in the risk factors. And so we can approximate LT plus 1 by the linearized loss LT plus 1 delta. The delta here has nothing to do with delta t, but it's this delta from option pricing. It's also known as the delta normal method, and the delta is the first derivative of an option with respect to the underlying, and that's why this has sort of given the whole thing its name, and that's why we have the delta here in our notation. LT plus 1 delta, the linearized loss over from t to t plus 1, is given by the time derivative, that's a constant, plus sum j equals 1 up to d of the derivative with respect to the risk factors times xt plus 1. And this is a linear function of the underlying risk factors. And that's maybe important because we will talk a lot about the distribution of linear factors of the underlying risk factor, of linear functions of risk factors, and one of the reasons is this linear approximation. So this is very old. This is sort of the ideas of the people who came up with risk metrics 1995, so 30 years from now, back in time. And they really used this together with simple rules for transformation of normal distributions under linear transformations to come up with a measure of the risk in JP Morgan's trading book. We do this now for a very simple example, as very simple stock portfolio. The idea of this example is, of course, not that this is a very interesting risk management application, but the idea is to explain the notation by a specific example. So we consider a portfolio of D stocks as 1 up to SD, and STI is the value of the stock at J, STJ is the value of the stock J at time T, and lambda J is the number of shares in the portfolio. Now, if you want to do a detailed modeling, the risk factors we would choose are the log returns of the portfolio. So the risk factor is the logarithmic price, and the risk factor change is then the log return. So if you take Zj as log of Sj, one reason for doing is that simply that allows us to work with distributions on the whole real line and instead of R+, which is a bit more convenient. Then we get the following mapping. The value at time t is just the sum over our D stocks, lambda j sj, or that's the sum over jogs lambda j e to the zj, ztj, because ztj is just log stock. And then the log is minus the change in value. That's minus the sum of all stocks of lambda j e to the power of ztj plus xt plus 1j minus e to the ztj. That's just a notation. And yeah, I get, okay, so that's the change in the value. And if I want to do that, then it's better if I walk here. Or otherwise, I feel like sitting in the cinema in the first row for 2 hours. That's the notation. Now, of course, this e to the ztj can be factored out. So lambda j to the ztj times the change in the value. We can write this slightly easier by introducing the weight WTJ as number of stocks times the current price. And so we can write this as a sum of these changes. This is nonlinear. This is not, does this work from here as well? Oh, that's nice. You get slightly better known formulas by looking at the linearized loss, LT1 Delta, where we have that the derivative of the exponential is just the exponential. So what happens is that when you compute LT1 delta, you get just this, this formula over here. Time derivative is not there. That happens only when you consider portfolios whose value depends explicitly on time, such as bonds or derivatives or loans. Our stocks do not. And we get this simple formula for the change in value, minus w prime xt plus 1. And of course, if you happen to know the mean and the covariance matrix of your log returns, then you can compute the expectation and variance of the one period loss very easily using standard rules for mean and variance of sums. So the mean is just minus w prime u, and the covariance, you get w prime, the covariance matrix of your log returns w. And if you assume, moreover, for instance, that your log returns are multivariate normally distributed, then you have characterized its distribution and you have evaluated the loss distribution already. So the first part of our job is done. And if it were not for all the deficiencies of the normal distribution, you could go home by lunchtime. Good. So loss distributions, what are, if we have computed loss distributions, what are important tasks in QRM? Now, if you want to do this, and if you're not happy with a normal distribution for your risk factor returns, you have to come up with a better model. And even if you are happy with the normal distribution, you still have to estimate its parameters. So you have to find a statistical model for xt plus 1. You have to compute the distribution function of LT plus 1, and then for various purposes, your answer needs to be a number. You need to measure risk, so you have to compute a risk measure, for instance, to know your regulatory economic capital, or to set up risk limits or anything. So that's basically the three tasks which you're having in this setup. And there are three broad methods to do that, and I go through them very quickly. We'll review them in detail on Wednesday morning when we discuss market risk. The idea of the analytic method, and that's sort of this old risk metric stuff and some extensions, is that you want to choose the mapping S and the loss distribution so that you can determine explicitly the loss distribution. The prime example is the variance-covariance method of the risk matrix group. The idea is, as I just said, risk factor changes are normally distributed. That is, of course, very much from the financial world. So the idea is that maybe the stock price follows a geometric Brownian motion as in the Black-Scholes model. Then log returns are normally multivariate, normally distributed. The second assumption is that linearization works, so that the distribution of the linearized loss is a good approximation to the true loss. Of course, that is clearly a market risk assumption. For that to be true, you need two things. You need to have that the probability that your risk factor, linearization always works only when you want to approximate small differences. So that means that the xt plus 1 should be typically small, and that means that you're looking over small time horizons, like changes in stock prices over 1 day, maybe 10 years. If you want to look over changes in stock prices or exchange rates over 1 year, that's going to be too large, and then you're going to have large approximations. And if you have a portfolio that is somewhat nonlinear, then this linear approximation will not work anymore. And of course, linearization works only when the mapping is not too linear. So that means that you maybe do not have too many very exotic derivatives or so in your portfolio whose price varies in a very nonlinear fashion with changes in the underlying risk factors. So this is really market risk. When the original JP Morgan risk metrics task was to come up with an estimate of the change in the value of a trading book over 1 day, and there this linearization can maybe be defended. Sorry, it was the wrong one. That allows us to model the loss as a linear function, and if you take these two assumptions together, what we have to do is we have to compute the distribution of a linear combination of multivariate normally distributed risk factors. The normal distribution is characterized by its mean and its variance, and we know that sums of multivariate normally distributed random random variables are univariate normal. So we know LT plus 1 delta is going to be normally distributed with this mean and this variance, and we're done. Well, advantages and disadvantages of such an approach. The advantage is that that's easy. So we have an explicit model for the loss distribution, and you get explicit risk measures. Two drawbacks. The assumption of normality, as you all heard in on many occasions already, and this will also be a theme of this course, is definitely not a good one. And it works, this linearization works only over short time periods. Now you could argue in defense of this method that it works for any class of distributions where we understand the behavior of sums. And this class of distribution is larger than the multivariate normal. This works for all so-called elliptical distributions, which we're going to discuss tomorrow, early afternoon, I think. And in this class, you have also more interesting distributions that can generate things such as heavy tails or the tendency of large movements in many components together. So this method could be extended for trading applications at least beyond the multivariate normal. But it's never going to work for typical insurance problems, so the horizon is 1 year. The second class of methods, and that is very popular with practitioners in market risk, is historical simulation. That's a fancy name or a finance name for bootstrapping, essentially. The idea is you look at your own loss history and let your estimation be guided directly by the empirical distribution function of these losses. It has two big advantages. It's easy, you don't have to do statistical modeling, and you really let the data speak, so to say. The empirical distribution function, if you have n observations, past losses, sort of, these are these L tildes, then this is the empirical distribution function. You take you take the proportion of all those observed losses that are smaller or equal to x, and that gives you an estimate of the distribution function of the loss over x. Now, what are these L tildes here exactly? That brings us back to this loss operator I introduced earlier. When you want to do that, if you have a loss, if you have a portfolio whose composition changes over time and whose value depends explicitly on time, you should not take simply the past P&L of this portfolio. You should take the P&L of your current portfolio given that the past risk factor changes occurred. So in particular, if you have, for instance, say a single bond, or let's take a single call option, say maturity date is at the end of the year, and you take, you're now here and you have maybe bought this option at the beginning of 2016, then you should not take the P&L of this option as you had seen it in the past, because now it's an option with about 4.5 months to go. At the beginning, it was an option with time to maturity of 1 year, and that is a different product. You should take the value of this option, the change in value of this option with 4.5 months to go, but assuming that the changes of the underlying, say it's an option, it's a stock option, so it's taking the last 6 months of changes in value or log returns on your underlying stock. That's the idea of this LTEL this year. The advantage is it's easy to implement, at least in principle, no estimation, no assumptions on models. The problem, there are two problems. You need sufficient amount of data. Now this is not so much of an issue when you talk about a single product, but when you talk about a large portfolio, we'll always have lacking data here and there, and then the method doesn't really work, or you need to make assumptions how to deal with situations where your data is not there, how to fill missing data points. It is purely backward looking. You just look at past losses. It depends a lot if you've, so the issue is have you seen in your sample of losses, you take maybe the bank 1 or 2 years back in time, and the issue is really, have you seen enough in the last 1 or 2 years so that this is a good guidance to what can come in the future. For instance, if you did historical simulation at the end of 2007 or so, the last 2 years, 2006, 2007, were very beautiful, quiet years on the stock market. Things were always going upward, volatility was small, so historical simulation would tell you that everything is fine. Of course, 2008 and 2009 were completely different. Remember, the financial crisis set on, and so this purely backward-looking measure wouldn't help you. Maybe if you would go back until 2001 or 2000 until the next the earlier crisis, you would see more, but then you have these data problems. So that's the issue why historical simulation is backward-looking, and the nice buzzword for that is that using historical simulation only is like driving a car by looking in the back mirror. Of course, a remedy to that, you could on the one hand try to do some statistical modeling that is more forward-looking, like some volatility modeling, or you could look at market data as well, such as implied volatilities, because they contain, of course, a feeling for the market if it's going to stay as calm in the future as it has been in the past. Also, markets can, of course, overlook crises, but it gives you an additional forward-looking idea. The second or the third thing is the Monte Carlo method. There you use simulation method. You don't look at past losses, but you'd have a statistical model, and you generate economic scenarios from that model and then evaluate your loss distribution out of that. It is quite popular in insurance, and you have lots of economic scenario generators. We're going to look at all of this in more detail in the context of market risk management on Wednesday morning. The second thing is, now assume that you have a loss distribution and you want to put a number on this loss distribution. You want to measure your risk, and this at the end always means coming up with a number. Now, why would you want to do this? Where does this issue arise? A risk measure, as I just said, is a mapping which sort of associates a risk, a loss, with a number. This issue arises in all amounts of capital calculations, be it economic capital or regulatory capital, because capital, the amount of capital you need is always going to be a number, and you're asking yourselves, how much capital do I need, or how much of this position do I need to finance with equity so that the risk is acceptable either for an external regulator or for the risk appetite of the company internally. You can also use risk measures as a limiting tool. So suppose you have a bank or maybe also an insurance company, and of course you have ambitious traders there and they think they know the market very well, and you think that also because otherwise you wouldn't have hired them, but still you want to limit their activity a little bit. And one way of doing that is by saying, okay, you may trade German equities as you please, but please make sure that the value at risk of your portfolio is smaller than 10 million or something. So as a limiting tool, risk measures are being used. And of course, in a sense, pricing of insurance, also finance, also requires you to put a number on risk. Approaches to risk measurement, let's go through this very, very briefly. So the idea of this slide is to go one step back, like that, and to see what types of risk measures are there, how can we classify them. One idea is sort of the notional amount approach. You say the risk of a portfolio is essentially equal to the size of the portfolio, to the sum notional values of the securities. Then we may say this is stupid. There are good reasons why, but it's still being used. Standardized approach of Basel II still does something like that, and there's also in the current debate, regulatory debate, are ideas that you should also look at the notion or the size of the balance sheet, which is basically the same thing. The problem is, of course, that you completely ignore such things as netting or diversification when you do that. Most risk measures which we find, we already mentioned value at risk or others, are in fact statistics of a loss distribution. So you look at the loss distribution and then have a distribution and try to measure the risk inherent in a loss distribution. Variance or volatility is maybe the oldest risk measure there. Value at risk and expected shortfall are very important. The nice thing about this approach is that it makes sense on all levels, so you can do this both for a single position or even for the P&L of an overall financial institution. It does reflect netting and diversification, of course. If you have two positions that cancel each other out, your loss distributions will have a smaller variance. A third approach, which is also in use, are scenario-based risk measures, and we will see later that this third approach and the second approach, even if they seem to be completely different now, are in fact somewhat linked by a general theory. Scenario-based risk approach, there you come from stress testing, say maybe as this stress test for the European banks, which happened a couple of weeks ago. So, but to really, or you find this idea also very much when it comes to computing margin requirement for trading at exchanges. Wrong one. You consider potential future risk factor changes or scenarios, for instance, a 20% drop in a market index or a certain interest rate environment or something like that. And then you say that the risk of the portfolio is the maximum loss under all scenarios. And maybe you also weigh down certain of these scenarios. The idea of weighing down is, say, this is a very hypothetical, very extreme scenario, and I don't want to take it into account 100%, but I still want to see what happens to the portfolio of this bank or insurance company under that scenario. Good. So how can we write this down, given the formalism we have introduced so far? X1 up to Xn are the risk factor changes or scenarios we might consider: the drop in interest rates, the drop in GDP, whatever, the hurricane or earthquake in Tokyo, or this type of scenarios. And each of these ones is given a weight which could be considered as a measure of its plausibility. The weights are between 0 and 1. And the risk measure is then the maximum overall scenario of the loss. L of xi measures the loss given that this scenario occurs, and we may weigh it down and we take the max of all these numbers. As an example where this really happens, you find it in detail in the book, is the standard portfolio analysis of risk, which is being applied at the Chicago Mercantile Exchange. There the scenarios are easy to define. You are trading futures on certain indices, and so you have up and down movements, and if it's also derivatives, so also up and down movements of volatility and certain combinations of those. It's a narrow set of, I think, 14 scenarios. Good.
That's also what the standard formula of Solvency 2 does.
It does also such things, yeah. X is a scenario and you assign it a certain probability, sort of. The idea is if you, it does make a difference, okay. It does make a difference if you compute the loss, say, take banking, the loss of your portfolio given that interest rates rise by 5%, and you say that's very unlikely, that's why, then you make a certain, well, whatever, profit or loss. Say you make a loss, and you have a loss of 100 million, and then you say this was a very extreme assumption, so in computing this maximum, I weigh down the loss. If you would move the W inside, say the W is 1/3, then you would not consider an interest rate change of 5%, but only of 5/3, so 1.7%. The xi itself is a vector of changes, and you assign it a certain probability, which is the W. Now, each of the W is between 0 and 1, and so 1 minus W is the probability that it does not happen. W is the probability sort of that this risk factor change happens, and 1 minus W is that it doesn't happen. They don't sum up to 1 directly. Good. So mathematical interpretation of this. Good. So L of 0 is 0, so if nothing happens, your portfolio value doesn't change. If delta t is small, that's fine. Then you say, as I just mentioned, W L of xi, you can write this as Wi L of xi plus 1 minus W times L of 0. And you can view this as the expected value of L of x when you say the probability that this risk factor change happens is maybe 1/3, and the probability that it doesn't happen is 0.7. This is not the true probability, it's something which you artificially assign. And then you can write this weighted risk measure, which we've seen here, this max here, as slightly more abstractly, as the maximum of the expected value of the loss under certain probability distributions, namely these here, where you say Pi is that with probability Wi, we see the change delta xi, and with probability 1 minus W, you see nothing. Now you may ask yourself, why on earth do I have, okay, I understood the simple formula, but why do I have to write it so complicatedly? The answer is that this complicated way of writing it is a way in which you can sort of write every risk measure which belongs to a certain class, namely the so-called coherent risk measures. And this weighting down of certain scenarios is also something that happens in real applications like this bond portfolio. Good advantages. It's a completely different setup first. Of course, it's particularly useful, of course, for making margin requirements. There you have to be able to compute quickly, and you can define the scenarios easy. It's a different thinking. You ask yourself really more, what happens to my portfolio if this and that happens, which is, of course, very useful complementary information. So that's the advantage of this type of approaches. The challenge, I wouldn't say it's a disadvantage or a drawback, but the difficult thing is, of course, what are the right scenarios to consider, and this can lead to endless arguing. And for instance, in this European stress test, banks said, well, we know that we were not particularly good at this stress test, but we think the scenarios the regulator picked are not really representative for the dangers we are facing, and you can argue all the time about that. Good. Now let's look at a very specific risk measure, value at risk, which is very popular in banking and insurance, and which is a risk measure based on the loss distribution. So for loss L, the value at risk at the confidence level alpha and 0 and 1 is the smallest number such that the probability that the loss, smallest number x, such that the probability that the loss is smaller than x is bigger than alpha, or the probability that the loss is smaller than x is smaller than 1 minus alpha. So in statistical terminology, it's just the alpha quantile of the loss distribution. Most of you know it. Probably for those who've seen it sort of for the first time, it may be useful to look at the following picture. If this is the distribution function of our loss here, then to compute the value at risk at a confidence level of 95%, you have to look for that threshold such that the probability that the loss is bigger than the threshold is 5%, or the probability that you're smaller than the threshold, so that's the white thing here, is equal to 95%. And if you move your confidence level further up, so if you go to 99%, say, then you need to have 1% mass to the right or 99% to the left. The idea where it was first done is in 1994 in the Weatherstone 415 report. I should explain maybe the terminology because this was already old when I was young. The idea is Weatherstone was the chairman of JP Morgan in those days, and he wanted to understand better. It was the time when derivatives were really coming up, the risk he had in his trading book, and he wanted by 4:15, so a little bit after the market closes and before he went home or to the golf court, he wanted to have a report on the riskiness of his portfolio, and ideally a number. And he wanted it by 4:15 in the afternoon. That's why 4:15 report. And to meet this challenge, this risk metric group developed this idea of linear normal distribution based modeling, and then they had a normal distribution describing the P&L of the portfolio, and to summarize this into one number, which they could present to the CEO, they came up with the concept of value at risk. Now, what is the most important sort of drawback of value at risk immediately without going into a deeper theory? Well, it's not a what-if measure. It tells you, okay, the value at risk of your portfolio, say the value at risk of JP Morgan over one day is, let's take a number, $50 million. This means that with the probability, say at 95% level, with the probability of 95%, they will not lose more than $50 million. Well, that's nice. But what happens with a probability of 5%? What happens if you go beyond that threshold? Is it then most likely that you will lose maybe $55 million, or are you then do you then have some very exotic products in your trading portfolio that can create losses only very rarely, but if then they hit really big, maybe some weird securitization deals or something, and then you're ending up with whatever 100 or 200 million losses very quickly. And value at risk, at least if you fix one confidence level, one alpha, doesn't answer that, which is of course a problem with this measure. Example, so that's just very quickly, there we compute the value at risk for normal and the t-distribution in this example. If x is normally distributed, then you can immediately, and this is not specific to the normal distribution, it's clear from the definition of value at risk as a quantile that if you scale and center a distribution, then the quantiles are also being scaled and centered. So the value at risk is just, if you take a normal distribution with mean mu here and variance sigma squared, of course, if you subtract mu divided by sigma, you get a standard normal distribution. and the quantile is just the mean plus the standard deviation times the alpha quantile of the standard normal distribution. And this is not specific to the normal. This holds true for every distribution. So you can sort of move centering and scaling outside computing quantiles. And so it's given by you have to need the mu, you need the sigma, and then the alpha quantile of the normal distribution. The same thing also works for the t-distribution. The t-distribution is also a symmetric distribution. Many properties are similar to the normal, but it does have more mass in the tails. And the value at risk also has this property here. Now the t-distribution has so-called power tails. We'll learn about that more tomorrow. And then it's very often a reference example which tells us how much will go wrong if we work with a normal distribution, but the reality is more heavy-tailed. Some thoughts on how you might choose delta t and alpha. That depends on the application. Delta t is the time period over which the portfolio is held unchanged, more or less. So in trading application, it's going to be short, 1 or 10 years. In insurance, it's typically 1 year because that's the amount of time you're sort of being bound to your contracts. Alpha depends on the application. Yeah, in the market risk, alpha is 99%, 10 days, 2 trading weeks. For credit and operational risk, you go further out on the tail. In the same time, you're looking at a time horizon over 1 year. So these two become very challenging statistical problems. If you want to so-called do backtesting, so you have your risk model and you estimate value and risk, and you want to see if the numbers which you're producing are somehow reasonable, then you might have to test at your models at lower confidence levels, because if you want to check value at risk at 99%, and this means on average you should have maybe 1 or 2 days per year, if you do it on a daily frequency, where you get a loss which is larger than that, that's difficult to test. You have very few observations. So if you whereas if you go to a 95% level, you should have more frequent violations, and you should also see this more often. Now, Paul mentioned communication in his introduction. When you want to explain value at risk to whatever your CEO or so, then you would say, okay, it's the amount, such the probability that we lose more than that is strictly smaller, say 99% value at risk. It's the amount of capital we need to have sort of or a threshold on our losses, so that the probability that we're going to lose more than that is smaller than 1%. Of course, you shouldn't take this all too literally. It's more a statistical quantile of the loss distribution. On the one hand, because if you assume that the portfolio is not changed, you assume that your model is correct, and you sort of assume, well, if you really had such a big loss and you wanted then to say, okay, now we have this big loss and we want to get rid of our position, if you really try to get rid of a big position in a difficult moment on the market, you lose probably much more because of lack of liquidity. This is not in this value at risk measure. So this idea, okay, our 10-day value at risk is like that, and okay, over these 10 days we can just close our position so we cannot lose more. That's of course quite wrong. Good, this is just a little bit of formality about generalized inverse. We don't really need that. Maybe it's better to look at this picture. Where I said the value at risk is the quantile, so it's the infimum of the set of all x such that fL of x is bigger or equal to alpha, and we call this the generalized inverse also of f. Computing it is very easy if you have strictly increasing and continuous distribution functions, but there are also other cases, and this slide is just there to illustrate what happens then. in the case that, so we're having some alpha here, and in the case that the alpha sort of, if you go then to the right and you sort of hit your distribution function at a point where it's continuous and strictly increasing, it's just the quantile, it's just the normal inverse. If the alpha is at a level where the distribution function has a flat spot, like here this alpha 2, then we are looking here at the left inverse, so it's the smallest number where this flat spot begins. And if you consider the alpha 1, if you're sort of looking at a quantile where the distribution function jumps, and for all these alpha, it's going to be this point here. So this means that whenever f is flat, like here, the generalized inverse will jump, because when you go from alpha 2 to alpha 2 plus epsilon, then you're immediately ending up somewhere to the right of this point here. On the other hand, whenever you have a jump in FL, so a point mass, the generalized inverse will stay constant, because whenever you vary alpha from here up to this alpha 2 here, the quantile function will always be constant. These things, when you, in particular when you come to the copula, when you want to do mathematically precise results, they can be a little bit annoying and you have to worry about them. At first reading, it's typically best to think that all distribution functions are continuous and strictly increasing. Then you don't have to worry about it so much to get the basic concepts. And otherwise, think of this picture. Value at risk appears a lot in risk capital calculation. It appears, for instance, in the market risk or in the regulatory capital calculation for the trading book. Maybe also go to the other side. Good. So if a bank uses an internal model for the market risk, the daily risk capital formula is given here. The risk capital at time t is the maximum of the value at risk over a period of 10 days at a confidence level of 0.99. So that's the value at risk you estimate today, looking 10 days into the future. And an average over the value at risk numbers, again, always 10 days into the future, of the last 60 days. And this average, you don't just take the average, you multiply it with a so-called multiplier k between 3 and 4. This multiplier means that unless if you're in a very, very stressed period, this sort of term wins because you multiply this by 3. So most of the time, this is going to be your market risk capital, and this is designed with the effect that by value at risk the value at risk itself will fluctuate a lot. The average over 60 days will fluctuate much less, and this means that also your capital requirement will fluctuate much less. Of course, you do not really want a largely fluctuating capital requirement, because then this could force you to raise new capital, which is extremely difficult in current times, or very quickly reduce your position to comply with regulatory constraints, which is also not very good. That's a little bit the idea of this formula here. This multiplier is also very important, because if regulators inspect the bank and if they find that the market risk system is not quite good, then they raise the multiplier between. So if your market system is very good, you have a 3, and then if you have problems, you may be getting a 4 there. Good. You find value at risk also, the purpose of this slide, it's a lengthy but very easy computation, is simply to tell you that the solvency capital requirement, as written in Solvency II, is the amount of capital that enables an insurer to meet your obligation over a time period of 1 year with a probability of 0.995%. If you write that down properly, you see that the solvency capital requirement is nothing else but the alpha quantile of the loss distribution, when now, because we're working over a period of 1 year, we introduce some discounting. That's what this slide says. So also the insurance world is working with value at risk. This has already popped up a little bit on some of the earlier slides. It is in the current regulatory debate, and I think also Paul used it already. An alternative to value at risk, which is the so-called expected shortfall or average value at risk. In the book, we use the terminology expected shortfall. For a loss, now we need a small assumption. Expected shortfall works only for losses that are integrable. The expected shortfall at confidence level alpha is defined as the average of overall value at risk levels from alpha to 1. So this is a normalization, and this is this. So this is the average value at risk level. So this definition would suggest to call it average value at risk. Why we still stick to expected shortfall will become clear later on. One thing is clear from the definition. You take an average over the value at risk overall. Of course, value at risk is increasing in the confidence level. So all these numbers are bigger than the value at risk at confidence level alpha, which is the lower bound of this integral. So the expected shortfall should be bigger than the value at risk. One first idea of explaining why one should choose such a risk measure is the following. Well, you could argue what confidence level should I take? Should I take 95%? And I don't really know what happens beyond 95%. Should I take 99%? Same answer, shall I go further into the tail? Then maybe I'm too far out there. It's difficult to pick exactly one level and say that's the right level. So why not just take an average over all of them? And this will allow us to, this allows you to look further into the tail. This is also called a what-if risk measure. Again, this is terminology which needs to be explained. You're asking simply what happens if my loss is bigger than value at risk, because say you have the confidence level alpha fixed, and you're also looking at what happens if I'm exceeding if I have a loss that is bigger than that. Maybe you then also start asking yourself which scenarios might be responsible for that and all these type of things. That's why you call it sometimes what if thinking that underlies expected shortfall. It's also severity based. It's not a pure frequency measure. You're not asking how often do I see a loss that is bigger than X, but also how large might this loss then be. These are all nice things about expected shortfall. Of course, it's more difficult to estimate because if you want to use this definition, you would need to be able to estimate all quantiles. It is more sensitive also to maybe misestimation in the tail. It can be problematic when you're having really heavy tail distributions which are close to infinite mean. Maybe they still have a finite mean, but just about, then if you try to estimate expected shortfall, you will get very varying answers. And it's also more difficult to test than value at risk. Good. Sub-additivity and elicitability, we'll come to that later. So forget about that point at the moment. The next point is just a few numbers. So we consider this example of our stock portfolio. And now we have only one single stock. The value of the portfolio is 10,000. If you may want, you can think you have also one share in there, but it can also be more than one share. The value of the portfolio is 10,000. The linearized losses minus ST times XT plus 1, where XT plus 1 is just the log return. And we assume that the log return is either normal or t-distributed. And the analyzed volatility is 20%, so the volatility from one day to the next, assuming 250 trading days, is given by this sigma number here. And we compare two distributional assumptions, a normal and a t portfolio. And the t portfolio is scaled in such a way that the variance of both distributions is the same. The mean is in both cases new. So we compare two different distributions with the same mean and the same variance for the log return, but with different tails. And this one is the one with the heavier tails, and that's why very often considered more dangerous. And In the following picture, we just see the value at risk and the expected shortfall. Both can be computed explicitly for the situation. So here we have 1 minus alpha. So as we go from here to here, we're looking further and further in the tail. So this would be alpha equal to 95%, and so on. So this is equal to 99.9%. Good. This gray line is the value at risk for the normal model. Of course, it's increasing as we make alpha larger, so 1 minus alpha smaller. The blue one is the expected shortfall for the normal model. Expected shortfall is higher than value at risk as it should be, but we see for the normal model that the difference becomes smaller and smaller as we go further and further into the tail. And we'll learn tomorrow why that is the case, that this is not just by chance. And now the orange and the red lines are for the T model. That's the value at risk, and that's the expected shortfall. Again, the expected shortfall is higher than the value at risk. But what is, of course, interesting is to compare the two risk measures across distributions. What we see is that at some point, if you look at value at risk as of here, the value at risk for the T model is higher than the value at risk for the normal model. If you're looking for moderate alpha values, it's the other way around. For expected shortfall, it's the same picture. However, there, because the expected shortfall is more tail sensitive in the T distribution as the heavier tail, the difference arises already earlier at lower confidence levels. That's what this picture basically means. And here this shows you how to compute expected shortfall and value at risk explicitly. There are not many. Okay, yeah, maybe the first line here is worth looking at. So we take the expected shortfall on the value at risk for a standard normal distribution. Expected shortfall also has this property that it's invariant under scaling and not invariant if you scale and center, then the risk measure is being scaled and center sort of as well, because it's an average over quantiles. Good. So we look at a standard normal distribution. That's what we have to compute by definition. Now, if you make the substitution x equals to phi to the minus 1 of u, and remember from basic calculus how to do these things, you immediately see that you get this expression here. So it's the integral from phi to the minus 1 of alpha to infinity of x phi of x dx divided by 1 over 1 minus alpha. So that's what you have to compute. And because you know this integral can be easily evaluated, you know the primitive, that's the answer you get. You can do the same computation for the t. What is interesting, okay, why is this first line here interesting? This substitution is sort of interesting because it tells you something. If you look at this expression here, how can you view this? This is the expected value of the loss taken over the period where the loss is bigger than its alpha quantile, and here you normalize it by that probability. So this expression here is nothing else but the expected loss given that the loss is bigger than value at risk. So the expected loss E of L given that L is bigger than value at risk. And this is correct not only for the standard normal distribution, but for all distributions who have a continuous distribution function. And here you see an easy proof for that, because this is all in this substitution, and that works for all distribution functions that have a density. So here you see a very easy proof for that for the case that you have a density at least. We've thrown out the more general proofs. That's why I wanted to show it on this single line here. And that explains maybe also a little bit the name expected shortfall better. You can look at the limit of these two, and you see that the limit for expected shortfall and value at risk in the T model is nu over nu minus 1. Again, it will be better to come back to this tomorrow when we look at tails of distributions in extreme value theory. And for instance, if we take typical nu values, we get that expected shortfall is maybe 50% larger than value at risk in the limit. And the conclusion, and that's a message which is true, if you have losses which have power tails, which are heavy tailed, and that's clearly the case in many financial applications for all financial losses, that's true, at least over short time horizons, then the difference between value at risk and expected shortfall matters in numbers. This proposition is what I just meant, this alternative interpretation of expected shortfall. If the distribution function is continuous, the expected shortfall can be rewritten as the expected loss, given that the loss is bigger than the value at risk. One easy way to see this is via this substitution, which I've just shown you. A more general proof can be found in the book. Now, of course, this explains the name expected shortfall. It's sort of the expected loss, given that you have a shortfall, so given that your loss is bigger than value at risk. You may ask what happens for discontinuous distributions. Well, what happens is there comes an additional correction term, which is a bit ugly, and that's why it's not here, at least not in this early stage of the course. If you want to know how the formula looks in general, you have to read chapter 8 from our book. I think we omitted it here because it's summer and there shouldn't be too many ugly things on these slides because they're being filmed. Good. So I've shown you two examples for risk measures, expected shortfall, value at risk. You could think about variances and so on. So you have a whole zoo, and you might ask yourself, well, what are good, what are bad risk measures? Which ones should I take? Maybe in practice, you don't ask that so much. You ask, what does the regulator want me to do, and how can I come up with the reasonable numbers? But of course, in academia, these are the type of methodological questions people tend to jump on. And so it was not surprising that soon after these first risk measures were being used in practice, and soon after regulators came up with Basel I and market risk amendments and so on, a theory of risk measures came up. And there are various theories, and these theories, well, the basic approach is the following. You start taking a step back from specific examples and ask yourself, well, what are desirable properties a risk measure should maybe have? Let's put up, well, call them, they were called axioms in this literature, so let's call them axioms. Then you can put up such a list, and then you can look at specific examples and maybe show if they do or do not fulfill these, or maybe fulfill these under certain specific additional assumptions, and then say maybe this risk measure is not so good because it does not satisfy this or that property. Then you can maybe even go one step further and try to come up with a mathematical theory that describes all risk measures that fulfill a certain class of axioms. And exactly that has been done, and this has led to the theory of coherent or convex risk measures. And sort of the two pioneering seminal papers in this literature in the context of financial risk measures are Arzner, Delban, Eber, and Heath for coherent risk measures, and Vollmer and Cheat for convex ones. But it should be said that many very similar ideas and also similar mathematical arguments exist in the actuarial literature on premium principles. It's more or less the same thing, and a theory of premium principles has already also existed. There's been some duplication going on. Good. Good. So for this theory, risk measures are defined in a linear space of random variables. So the idea is, okay, this risk measure assigns a number to a set of losses, and we assume that these losses are linear space, so we can add and subtract them, and constants are also in there. We can multiply them with constants, double positions, and associate a number to them. This space, calligraphic M of random variables we consider, there are two potential interpretations. On the one hand, we may interpret them as losses, as we will do in this course, fitting, and then that's sort of the amount of capital you need to back a position with loss L, or you ask yourself, how much of this position do I need to finance with equity and how much may I finance with debt, so that the whole situation is acceptable. Alternatively, we can view them as future value of the position, and then you would view the risk measure as the additional amount of capital you need to add to the position to make it acceptable to a regulator. This distinction matters because depending on the interpretation you choose, you will get different sign conventions in certain of these axioms, and unfortunately not all books or all texts use the same sign convention, so when you switch from one to the other, you have to check these axioms and the interpretation they're working with. You can translate them, but as always, I mean, as Freddy Delban, who invented part of his theory, said that the human brain is not able to multiply more than 3 times in a row with -1, and that's the times of problems you're running into when you switch from one interpretation to the other. Good. We'll stick to the second interpretation in line with the notation of our book. So rho of LT plus 1 is the total amount of capital necessary to back a position with loss L. Good. These axioms. The first axiom is monotonicity. If you take L1 and L2 and they are ordered so that L1 is always smaller than L2, so in every state of the world, when you have portfolio 1, you will lose less than when you have portfolio 2. Then you also need less capital to back this position. That should be clear. So L1 should be, a row of L1 should be smaller than L2. That's sort of, I think everybody would agree to that. The next one is the translation invariance. That sort of normalizes the risk measure a little bit. Rho of L plus small l, so in our notation, capital numbers are typically random variables, small numbers are constants, is equal to rho of L plus small l. So this means the following: if you consider a position 2 losses and the one is larger than the other one or is changed by the other one by a deterministic amount, then the amount of capital you need to back the second one and the first one, they are related in that way. This is certainly also reasonable. It basically means that you really measure risk in monetary terms. Yes? Anybody in here? No. Good, most people believe this to be reasonable. Well, okay. Almost all people believe this. Let me answer this as a probabilist. Almost all people believe this to be reasonable. This is reasonable almost, surely, yeah. Now, it means simply, yeah.
I think if the loss, if you consider a time period, then
you might add, discounting over longer time periods.
Over 1 period horizon, so there's some time value change of time
Good.
money, so this translation.
Almost all people would agree that if you look, yeah, that's for simplicity. If you really, it depends on the time horizon you're considering. Almost everybody would agree that if you go over longer time horizons, you would have to add some discounting there. But then after that, it's a normalization property. So these are the non-contested axioms. The third one is more contested. That's the so-called subadditivity. If you take 2 portfolios, the one leads to the loss L1, the second one leads to the loss L2, and if you join them, and then you can ask yourself, how much risk capital do I need for the joint portfolio? Is this smaller or bigger than the sum of the 2? And subadditivity tells you it should be smaller than the sum of the 2. And that reflects somehow the idea of diversification. The joint portfolio has maybe some net there. If you merge the 2 portfolios, there's maybe some netting going on and some of the risk might cancel out. So you shouldn't need more for the joint portfolio than you need for the two individual ones. So it reflects the idea of diversification. Another argument in favor of this type of axiom is that if you have, say, a bank or an insurance company and you have two sub-portfolios, L1 and L2, and the inequality goes the other way around and you have the feeling that regulatory capital is scarce, it might be optimal to break up the company into two smaller sub-companies and then you need less capital. At least, I mean, you don't have to change much, you just need to hire a few clever lawyers. That might add, okay, that might of course eat up the capital you've saved when their bill comes in, but never mind. And you wouldn't want to encourage such a behavior. And the third advantage or argument in favor of sub-additivity is it makes decentralization possible. I was talking about these risk limits earlier on. So say you're an overall, okay, let's say you're a very simple insurance company and you know that you have overall a risk capital of 500 million Swiss francs, and of course, and then you say, okay, on the one hand, we have our actuarial or underwriting risk, we have our investment risk, and each of them consumes some capital. I don't want to micromanage them. I believe that they know better what they should do than I as the overall manager. But what I have to make sure is that the risk they are taking is fine, sort of. So I tell the underwriting guys, you can have, you can do whatever you want, but the risk of your portfolio shouldn't be larger than 600 millions. And I tell my investment guys, your risk shouldn't exceed these 400 millions. And then if I have a sub-additive risk measure and put it all together, I know that the overall risk of my company is smaller than the 1 billion I have. And if it were not sub-additive, this might not work. That's the idea here. Now, well, I wouldn't call it a criticism, but of course, this axiom, one of the reasons people debated this axiom is that in certain scenarios, value at risk is ruled out. It's not always going to be sub-additive. We're going to see examples soon. Value at risk is monotone, translation invariant, positive homogeneous. That comes next, but in general, not sub-additive. Now, you could say, well, maybe that's not a criticism of sub-additivity. That's rather a criticism of value at risk, and that's the point I would take there. I mean, if you do this and you believe in this axiom, then you should take another risk measure. But there is another critical point to be made. Sub-additivity does not really allow you to penalize concentration risk. We come to this with the next axiom, the so-called positive homogeneity. Positive homogeneity tells you the following: if you take your position and double its size, then you need twice the amount of capital. Rho of lambda is lambda rho of L for all lambda positive. Good. The idea is the following. If you have a sub-additive risk measure, and if you take lambda equals, say, to 2, then of course you know a priori lambda of 2L is lambda of L plus lambda of L, and rho of 2L is rho of L plus rho of L. No, rho of 2L is rho of L plus L, and that is bounded by 2 rho of L because of sub-additivity. It cannot be larger than that. And because there is no diversification going on there, you require it to be exactly as large. That's the idea here. Now you might say, I don't like this. And that's maybe the true problem of sub-additivity. I think if I double my position, or if I take 10 times as much, whatever, CDO squared contracts on American mortgage loans in my portfolio, I should really need more than 10 times as much capital, because maybe I'm the only one on the whole world who has these things in his portfolio and I will never be able to sell them again. Maybe I should need 100 times as much capital or so on. So you would want to penalize concentration risk, and this is not done under positive homogeneity, and it's not possible if you have a sub-additive risk measure because you have this upper bound there. So in that sense, you could criticize sub-additivity because it doesn't allow you to penalize concentration risk. Well, and then this has really led to the idea of convex risk measures. risk measures where you say, I don't want this positive homogeneity and sub-additivity together. I just require that rho is convex, so rho of lambda L1 plus 1 minus lambda L2 smaller or equal to lambda L rho of L1 plus 1 minus lambda rho of L2. Every coherent risk measure is also convex. A coherent risk measure is a measure which satisfies these four axioms. So translation invariance, monotonicity, the uncritical ones, sub-additivity, and positive homogeneity. And every coherent risk measure is automatically convex, but it doesn't really penalize concentration risk. Some people said, well, maybe it's better not to require sub-additivity, but to require just this. This is maybe better capturing the idea of diversification, because what that true diversification does really mean, instead of saying, I'm taking only this risk or only that risk, I'm taking a convex combination, one half of this and one half of that. And that should be, that should require a lower capital. An example for a coherent risk measure we've already seen. That's this generalized scenario risk measure before, where we have the hypothetical loss under certain scenarios, and we say it's the maximum of the expected value of these losses under a certain set of probability measures. To check that this is really sub-additive, you simply use the fact that the max of a sum is smaller than the sum of the maxes, and that's the reason that drives that. The interesting part is sort of that there's another way around. So every measure that can be written in this way, expected value of the loss, and you maximize over a certain set of scenarios or probability measures, is coherent. The interesting part is that this is if and only if. The other way around is also true under some small technical assumptions. In the book you can find it in a complete and fairly elementary proof for the case of finite probability spaces. If you want to know more, you have to read papers by Freddy Delban or look into the book of Fellmer and Sheet, but it's essentially true in general for all risk measures, with some small measure theoretic additional complications. But as I said, we have a summer school and the weather is nice, so the weather is so nice, so we're not going to talk about that. But every coherent risk measure can essentially be written in that way. So,
but then typically with an infinite set of scenarios.
Typically with an infinite set of scenarios. Good. I already mentioned the idea of convex risk measures. Convex risk measures are those risk measures where I say, okay, positive homogeneity and translation invariance, they were uncritical, I stick to those, but instead of requiring sub-additivity and positive homogeneity separately, I merge them into this one axiom of convexity, and this gives me a larger class of risk measures, and in this class of risk measures it's possible to penalize concentration risk more strongly. For an example of an interesting risk measure which is convex but not coherent, yeah, you have to also look into our book, Chapter 8. You find that there in the first two sections. We had to make a choice, and these were a few of the things that had to go for reasons of time. Good. Examples. The most important example is expected shortfall. Expected shortfall is a coherent risk measure.
Excuse me, I find this really interesting about the convex risk measure.
Yeah.
Does it mean that you really forsake then this effect of being possible to be decentralization, the example that you gave with underwriting and
this would, yes, that would be lost. But on the other hand, you're able to penalize, say, concentrations. It always depends. I mean, there's a general answer. There is not one risk measure that does everything for you. So you really have to look what is more important for you. And also for the theory of capital allocation, positive homogeneity is, for instance, very, very nice. So there, also this Euler principle and all of that is also gone when you go to non-positive homogeneous things. When you really think that liquidity is very much of an issue, then it might be useful to go to more general convex risk measures, or of course to stick to sub-additive ones but work with liquidation values. I mean, with liquidation values, you can of course say, okay, I take a certain position, and in its value I do not take the book value, so the value assuming at its current price, but I take an additional discount for saying if I really have to get rid of this position, then maybe I have to take into account that prices will drop as well, and you can of course also work, in computing the losses, you can already work with liquidation values. How to do that exactly, how to estimate is a completely different story that gets you into market microstructure and optimal portfolio liquidation and all of that. That would be another summer school next year maybe, but good. Sub-additivity is also there, but that can be shown in various ways. You find it in chapter 8 of our book, one nice way. There you also find the so-called dual representation as generalized scenario. You see how the measure of probabilities sort of looks like and all of that. As I said before, we had to make a choice. Good. Well, it seems we're doing fine for time. If you allow me to run over maybe 2 or 3 minutes, then I can finish this section nicely. I already said value at risk is not sub-additive in general, so you have every right to ask for a few examples. There are many examples in the meantime, and you can look, you can group them. One type of examples might happen when L1 and L2 have very skewed distributions. We're going to see one of them. If you have light-tail distributions in small alpha, this may happen. For heavy-tail distributions, this is a very generic situation. And it may also happen if you have very nice, say, normally distributed risks, but you generate a very special dependence structure. Good. This example I will not talk about because I think, if at all, it should be discussed together with risk bounds on Thursday when we really know what it means to talk about special dependence structure. The other ones we can go quickly through. Exercise or example, skewed loss distribution, that's not very nice, it's an easy story. So you have 2 independent defaultable bonds, 5% interest rates, you can see it's an old example. And they have a default probability of, okay, so their current nominal value is 100. In 1 year, you get 105. And if the firm doesn't default, and if the firm defaults, then you get 0 to keep the example simple. And the probability of default, we assume we know it, it's almost 1%, 0.999, so it's a little bit below 1%. This choice is, of course, so that the numbers match for the example. Good. So what's the loss here? Well, with a probability of 1 minus p, we're going to survive. So 99.1% we're going to survive. And if we survive, we make a profit of 5. We bought the bond for 100. We can sell it for 105. So our profit is 5, so our loss is minus 5. And with a probability of P, we're going to make a loss of 100 because our current value is 100 and our future value is 0. So that's the individual loss distribution. And if you take alpha equal to 0.99%, the value at risk is minus 5 because the probability of losing sort of no more than minus 5 is even bigger than 99%. Now let's look at the sum. So we hold one bond of each firm. Each, you would say, well, if you have 200 euros or 200 Swiss francs, say, well, you could either buy 2 bonds of one company or you could buy 1 bond of every company. Of course, if their default is independent, almost everybody in the room would say, well, let's diversify and buy 1 bond each. But let's look what happens when you measure risk with value at risk. So what's the sum of the losses? It can be either minus 10, that is if both bonds survive, and that has a probability of 1 minus p squared. because 1 minus p is the survival probability, and that's 0.982. The loss can be 95. That's if one bond survives, and we make a profit of 5, and the other one defaults. So on the defaulting one, we lose 100. On the other one, we make a profit of 5, so the loss is 95. The probability of that is p times 1 minus p, and there are two scenarios, so it's 2 times p times 1 minus p, and 200 if both default. And if you now compute the value at risk of the sum, you get that it is equal to 95 because this 0.982 is slightly below 99%, so you have now you're sort of going into that quantile. So the value at risk of the sum is 95, so whereas the value at risk of each of them individually is minus 10. So if you compare the two portfolios, on the one hand, you buy 2 bonds of one firm, on the other one, you diversify. If you use value at risk at the 99% level, you would on the one hand require, for the diversified portfolio, you would require risk capital of 95 francs. For the non-diversified one, you would have value at risk of minus 10. That is, you could even take 10 euros or 10 Swiss francs out of your portfolio, and the regulator would still say, well, it's okay, man, it's a nice portfolio. Something is strange there, because you would say, well, I should diversify maybe here. And what is strange is exactly that value at risk in this example is not sub-additive. So that's the one example. It's the example with skewed loss distributions because each individual loss distribution is very skewed. If you look at it, you have a large loss of 95 with a very small probability and a small loss of 5 with a very large probability. So that's this skewed loss distribution. That's that.
Actually, to some extent, wouldn't that be very relevant for credit risk, where you have typically used Bernoulli distributions, which are very skewed?
In a sense, it could be relevant. Of course, it depends. If you have many bonds and so on, it might go away. But it could be relevant. I would say it's always relevant in a trading environment where you can sort of always create losses which have a very small probability, but if they happen, they hit very big, and then value at risk sort of doesn't see them, and you can always create these type of examples. And it's particularly relevant if you are, as I said, in a trading environment where traders can also sort of optimize against the risk measure they're being measured with. It's a little bit, well, that's sort of economic agency theory. It depends on if you take, also depends on the order in which you do things. If you first choose a portfolio and then measure its risk, and the person who chose the portfolio doesn't know in which way he or she will be evaluated, or if you sort of already optimize against a given risk measure and exploit these type of weaknesses. The second one is independent light tail distribution. So what we see here is alpha. We're going to see these are two exponential distributions. The value at risk of the sum is the black line, and you see the sum of the value at risk individually. And if the black line is above the blue line, then these are situations where value at risk is not sub-additive but super-additive. And this happens for small alpha. For large alpha, this goes away. And the next two examples I will skip in the interest of time, and we will come back to this whole issue a lot on Thursday, because you can really ask you sort of not only is value at risk super additive or not, but sort of by how much can this equality go wrong. And there's in the meantime a whole theory around that, and Paul is one of the people who contributed to that, and I think he will give you an expert's view on that on Thursday morning.
Is it worth doing the second part of remark 217? Just
Say. Co-monotone. Okay, that might be worth doing, yeah. Well, I think we're doing it anyhow later on. Value at risk can be sub-additive for special situations. That's this point. So if you take for the set M of losses, very special situations, value at risk can be sub-additive. For instance, if you take multivariate normally distributed random variables, or more general elliptically distributed random variables and linear combinations, then everything is fine. Maybe that is also historically one of the reasons why value at risk came up, because in this original risk matrix scenario, everything was sort of fine, and these type of examples couldn't happen. Well, in the world of multivariate normal distributions, everything is fine, and we're going to even have a theorem on that. And we will, I think it's also, yeah. Paul told us that we're going to do everything in credit risk on Friday, but some things will be done in the risk aggregation section on Thursday morning. Okay, but now I think it's time for lunch, and we meet again at 2 o'clock.